Confirmation regarding the audio, please, guys. If you're able to hear me out perfectly well, thank you. Yes, today is the day of equinox. That is correct. So, hello, a very warm good evening to all of you, and welcome to Byju's Exam Prep. Welcome to another session of climatology, where today we shall be focusing upon the aspects of air pressure. We shall be trying to understand what do we mean when we talk about wind and wind movement. What are the factors which end up determining how a wind moves in an area? Then we will be taking a look at the different models of air circulation which is observed across the world. That will give us an idea about the permanent wind system and also about the local wind system. After that, we shall be initiating the discussion for humidity and precipitation rather than directly going into cyclones. First of all, we shall be discussing about rainfall characteristics, etc. And then we shall be proceeding into the portion of cyclones. Now, what is it that we had discussed yesterday when we talk about pressure? So, yesterday we had discussed that atmospheric pressure is the overall weight of the air mass as it imposes itself on the ground surface. So, the weight that is imposed by the air mass, that is referred to as pressure. Now, depending upon the density of that air parcel or the air mass, that is something which controls the pressure that is observed or is experienced in any particular area. So density of air, that how closely are the air particles packed into it, that is a driver of air pressure. Now, we also basically looked at certain other facts that, for example, if in any area, for any conditions whatsoever, if an air parcel tends to rise up, let's suppose, when an air parcel tends to rise up, what will be the impact of on the ground surface for the pressure experienced? As the air parcel rises up, the pressure reduces. So we had seen rising air parcel reduces the air pressure, and simultaneously, anywhere where you have a sinking air parcel which is sinking, generally cold air masses and cold air parcels, because of their heavy weight, they are the ones which start sinking. Yesterday also, while we were discussing the portion of valley inversion, we talked about the fact that how the cold air parcels, because they are so heavy, they start sinking automatically. So always sinking air mass or air parcel. Air parcel basically refers to any column or any sample of air that we are referring to. Sinking air parcel or air mass increases the air pressure. Right? So these basic facts we had seen yesterday. Now we will take a look into how is it that winds come into existence in any particular area. What are the driving factors? What are the conditions which lead to wind movement occurring and experienced in any particular area? So here we will take the consideration of a pressure created due to temperature conditions. Temperature conditions, we have seen that wherever you have warmer air, That creates low pressure. Wherever you have colder air, that creates a higher pressure. So let us take a look into that. So suppose here I consider two different places. Let's suppose this place A. It receives lot of heating. Significant amount of heat is received. Now, if A is very hot, then what shall be the consequences of it? Just a moment. So, if we say that region A is very hot, what shall be the consequence of that? The air immediately, which is in contact with A, that air will also start getting hotter and warmer. So, this air which is in contact, this will also get very warm. Now, whenever an air parcel becomes very warm, means the particles which were included in them, those particles, they start a kind of a random motion, right? They start moving here and there. Many of them will escape the system as well. So overall, the weight of this air sample or air parcel, because of heating, you have many molecules which have escaped the system. So can we not say that due to heating, the weight of the air parcel has reduced? Now, if the weight has reduced and it is hotter as well, so what will be the immediate consequence? Anything which is lighter tends to rise up. So this being light will tend to rise up. It rises up. On the ground surface, what kind of pressure conditions will it create? It will create a low pressure. Right? Now, we had earlier talked about the fact that air density near the ground surface is the maximum. But here we are saying that the air near the ground surface is getting lighter. So that is because in the other areas, the air density might be absolute maximum. But in this region, because of the immediate heat which is provided, that is why you will have the particles following a kind of a randomized motion. And that is why you will experience the air to get significantly lighter. Now it rises up. Now, as it rises up, it moves into which area? Where the air density is less. As you move higher up with height, the density of air gets lesser. So that is where it will start to expand a bit. And in the process, whatever heat that it was carrying, that heat will be given out to the surrounding. Heat will be given out. And this will air parcel as it rises up because it is warm. It is warm when it gets in contact with the colder air above. It will give away the heat to the colder region. And in that process, the temperature will start cooling down. It will start cooling down. Isn't it? Now, meanwhile, as it is still cooling down, it will keep on rising up till what point? As long as it is warmer than the surrounding air, it will still be lighter and it will continue to rise. It will rise at the level of tropopause, that is the top of troposphere. Once it reaches the region around tropopause, it cannot rise any further. Why? Why can't it rise any further? Because air rises up as long as it is lighter than the surrounding. Until when will the air be lighter than the surrounding? Till it is warmer as compared to the surrounding air. So air rises up, as long as it is warmer than the surrounding. Okay. Now, when it reaches the region of tropopause, if it wants to rise even further, it cannot rise because above tropopause you have stratosphere. which is warmer as compared to the upper regions of troposphere. Stratosphere is warmer. So above tropopause, you already have warm stratosphere. You have warm stratosphere. Now, that is why the air won't rise any further. So think of tropopause as a kind of a ceiling. The air hits it, then where will it go? It has got no other place to go. So it will break and diverge into different parts, right? All the meanwhile, where the air is at the top level of tropopause, the temperature at the top of tropopause, will it be low or will it be high? It will be very low. At the top of tropopause, the temperature might be somewhere around minus 60, minus 70 degrees Celsius. So the air all the while gets cooled down further. So the air cools down further. Now, as the air cools down further, then what? Eventually, this cooling will continue till the air becomes very cold. Now, eventually, the air will become very cold. Now, when the air becomes very cold, what will happen to the particle density in the region? How close will the molecules be, or how far apart will the molecules be in this case? So here, despite the height or regardless of the height, because of extremely low temperature, here the air will have the molecules which start packing it up. It will start packing it up, right? So overall, this cold air will be very dense, will be very heavy. Now, when it is heavy, what will it experience? Automatic sinking down. So it is something which is going to start to sink. Now, when the air is sinking, there is slight contraction which will happen. There will be some amount of adiabatic heating which will also happen. But nonetheless, this air parcel will hit the ground surface. This will hit the ground surface. Now, in that region where it is hitting the ground surface, what will be the impact of pressure or the impact of air on pressure? So as it is going to hit the ground surface, it is substantially going to increase the pressure which is experienced, isn't it? So here you will experience a kind of a high pressure. It will experience a high pressure. Now, in this region of high pressure, what can we conclude with regards to the abundance of particles or molecules which are present? We can say that in this region of high pressure, there's an abundance of air molecules and air particles. We can say because the air is sinking there, air is hitting the ground surface. So we can always say there is an abundance of air particles. Conversely, what can we say with the portion of A, where the air has been rising up? So because the air has been rising up at A, can we not say that at the ground level there's a kind of a vacancy which is created? So at A, there is a vacancy of air particles created due to rising air. At B, there's a surplus of air particles created due to sinking air. One place of surplus and one place of deficiency. So automatically air will rush towards the region of deficiency. And this movement of air, that is when we actually get to feel air. Otherwise, when you are sitting in the room, rarely will you get an observation that, okay, there is so much air around me. This is nitrogen, this is carbon dioxide. I will not take in nitrogen today, I will only inhale oxygen. That kind of a sensation, I hope that none of you get that. So air cannot be felt naturally. Air is felt only when it starts moving. You feel the wind, you feel the breeze on your face. So that is when the air starts to move. This is what is referred to as wind. But if you zoom out of this scenario and then take a look at the larger picture, the larger picture tells you a story that we have seen unfold even in the region of mantle while studying geomorphology. And that is the story of heat distribution via movement of particles. And that is what circulates or generates a kind of a convective current in the region of tropopause, a kind of a convection current in the region of tropopause. So, overall, in the region of tropopause, you can observe that in the region of low pressure, first of all, air warms up and rises, it distributes heat to the surrounding area, and eventually, after spending some time at that height, air cools down, starts to sink, exerts high pressure on the ground, and this is where you will have wind moving from a region of high pressure to a region of low pressure. This is how the air circulation takes place. Okay, right? Now, now we come to the thermal and dynamic pressure zones. Now, this is something which is going to be relevant for your further understanding of the various different pressure zones that we have to study, of the various different pressure zones created on the planet Earth. Uh, Prakash, is high and low pressure zone only reason for blowing of wind? Absolutely yes. Wind will not blow without the existence of a high or a low pressure region. There has to be a difference in pressure for the air to start moving. For example, take the case of water. If you have two vessels at the same level, will water ever flow from one to another? Never. Even for water to flow, you need to provide what? A kind of a height gradient. Without height gradient, water will never observe a kind of a flow. Now, that height gradient is created by the mountains, in the case of the rivers, by various other factors. Even if you have to pour a glass of water from a jug, what do you do? Do you keep the jug at a lower level and glass at a higher level and it automatically fills up? No. You have to lift up the jug and then pour it. So, again, you are providing a kind of a height difference for the water to flow. Similarly, for current to flow, you need to provide difference of charges for the current to be flowing from one region to another. In the same way, for the air to flow, you need to be able to provide difference of pressure. That difference of pressure is very instrumental in initiating wind movement at all. Okay? And Mupkalvar, does always pressure move from high to low? Pressure does not move from high to low. Wind moves from high pressure to low pressure. Why it is said that upper layer has less density, though we have cool air? Does that mean more density? No, not at all. See, all those who are getting confused in this, suppose this is the upper region of troposphere. This is the ground surface. Density is always maximum near the ground surface, is maximum. Now, if I say that upper air is cold and upper air starts to sink because of high weight, does that mean that its weight is higher than the air at the ground surface? No. That means it is heavier than the air around it. Just understand that near the ground surface, close to around majority 80% of the mass of troposphere, that also is something which is restricted only closest to the ground surface. When you say that the air is denser and sinks, or the air is lighter and rises, that is always in comparison to the surrounding elevation air, that what is the temperature experienced in the surrounding. Okay. uh Raktim, I'm unable to get your question. Pressure is created, Mohammed, as a result of the weight imposed by the air. Now we come to thermal and dynamic pressure zones. So, yesterday, while carrying out a discussion, we had held the discussion that pressure is not always controlled only by temperature. Even though temperature is a major factor for controlling and determining pressure. In certain area you can have low pressure due to warming. Certain area like poles which are very cold, there automatically there will be a high pressure. So in certain areas temperature is a major factor, major determinant, but it is not the only factor determining the change of pressure. So when we talk about creation or imposition of low pressure or high pressure, it can be controlled, or it is something dependent on two factors. So pressure is dependent on two factors. One is temperature and second is movement, or rather dynamic movement of air. Rahul, temperature is proportional to pressure. Uh, Temperature is proportional to pressure in high. No, see, Rahul, okay. So if you are getting confused in this, that means you are getting your mind adulterated with the thermodynamics that you might have read in your physics, right? That is where you see PV is equal to nRT and you rote learn the fact and you simply drink it up. So throughout your life, even if someone wakes you up and asks your name, you will say PV equal to nRT. Correct me if I am wrong. But in all those thermodynamics, if you analyze, all these conditions are basically done in a closed system. When we consider the temperature to be distributed in the atmosphere, and there we have the influence of the ground surface, and there the temperature can easily be lost by air in the surrounding, that is not a closed system. That is an open system. So in an open system, pressure and temperature don't follow the same proportionality. I hope I'm making sense, because if I have a closed system, if I will compress it, air will get squeezed, pressure is increasing, temperature is increasing. Now imagine if I unfold it from the sides. If I increase the pressure, what will happen to the temperature? The air will simply escape from the sides. So that is the difference in between the ideal conditions of thermodynamics that we are supposed to rote learn in our school days and the realities of atmosphere. I hope you are aware of that. Okay. Raktim, my dear friend, do write to me once if you want, and please specify your name in the subject itself. It is highly probable that your mail might have been lost in the milieu, so please write it up again. And trust me, I'll get back to you tonight itself. So just in the subject, write your name. Now, I hope, Rahul, now the situation is clear. Okay, this is not the ideal temperature pressure condition. So the atmospheric pressure that we see, which is exerted on the ground surface, that is dependent on multiple factors. One is temperature, other is dynamic movement of air. So there are certain areas across the planet where you have the existence of a high pressure and low pressure purely because of the influence of temperature in that area. For example, the polar region. Polar region is extremely cold. Now, because of extremely cold conditions, there will automatically be a high pressure which is imposed, right? So, automatically, the polar region always perpetually will experience high pressure. Then, in the equatorial area, always the angle of solar insolation is almost perpendicular. So there will be greater heating. So mostly you will experience the existence of low pressure there. So that is what is referred to as a thermal pressure zone or a thermally induced pressure zone. So when we talk about thermal, this is where pressure is imposed due to influence of temperature on the ground surface. So here, because there is influence of temperature, hence thermal. Now example, perpetual presence of high pressure region around poles due to extremely low temperature. Low temperature. Okay, so that is thermal. We have seen warm air rises up, cold air sinks down, creates a high pressure and low pressure. That is thermal because there is an influence of temperature taking place. Now, what do we mean when we talk about dynamic? Dynamic means something which is mobile, something which is experiencing a kind of a movement sometimes. That is what is dynamic. So, I will give you a scenario here. Let's suppose I give you the room. Let's suppose. Biswajit, angular inclination and high albedo, how will they influence the pressure? If you are saying they will also influence the pressure, how will they influence the pressure? What will high angle of inclination do, or what will the low albedo and high albedo do? Eventually, they will influence the temperature, and that temperature will influence the pressure, isn't it? So that is where we have written pressure is induced by temperature. Now that temperature can be impacted by presence of cold currents, warm currents of the ocean, depending upon the altitude of a region, depending upon the angle of inclination. That temperature can be controlled by many factors, right? But then the prime role or the prime reason why a high pressure or a low pressure is created is very simple: impact of temperature. Now here, when we talk about dynamic, here you have the impact due to movement of air. So for example, when we say that, let's suppose in this room, we have air which is moving near the ceiling. Let's suppose the room that you are sitting in. Whichever room you are sitting in right now, let's suppose air is coming from both directions in the ceiling and is colliding. Where will the air go when it is colliding? And continuously you have attached a kind of a fan here. So continuously, it looks more like a bunny, but let's suppose this is a kind of a fan which is indicated. Let's suppose on both sides, you have basically installed large fans, and these fans are giving out significant amount of air. So there is a consistent provision of air, and the air is colliding on the ceiling. So what do you think will happen? Will the air simply crisscross each other and reach the point A and B? Will the air eventually blast through the ceiling and go somewhere, maybe D? Will the air start accumulating here and eventually be heavy enough because of surplus of air created in this region, and they will start to sink underneath and maybe reach the portion E? So which of these events do you think is going to unfold if you have the movement of air something like this? What do you think? Beautiful. It will sink. I'm happy that nobody is saying it will go D. Right. Right. So it will reach here, that is E. Air will collide, it will sink, and it will reach there. Similarly, when we talk about the planet Earth, and let's say here you have the tropopause or the top of troposphere. Tropopause. It is absolutely possible, and that happens in certain areas, as we will take a look at, that air at a higher elevation, in certain areas, they will collide. And once they collide, they have no other pathway to go but to start to sink. Now, when they are sinking, after they hit the ground surface, where will the air go? Again, I will give you the options. Let's say the air has hit the ground surface. Will it then drill into the ground surface because there is so much of air, and will it reach somewhere underground in F? Or will it simply start dividing itself and move towards the region C? What do you think will happen? Good. It will divide itself. So here also on the planet surface, as the air hits the ground, it will divide itself. It will start diverging, isn't it? Now let's suppose this air which has diverged, it is moving in its path. It has just now come from the top of troposphere, and this air wants to explore the surface. So it is exploring the surface. It is moving through mountains, valleys, and so on. Now some other region experiences movement of air in the same area. Now here, when the air collides, again, if I were to recreate a similar scenario, let's suppose in the same room that you are sitting in, now someone, what they have done is, they have installed large fans near the ground surface on both sides. And they are giving off winds near the ground surface. Now these winds are coming over with a significant velocity. Now where will they go? Will they, because the winds are closer to the ground surface, they are feeling lazy, so will they dig deep down and will they reach A? Will they start bypassing each other? Where the wind is coming, they will take a side, a left or a right, and will they meet each other at A and B directly at the fan source? Or will they start accumulating here? And eventually, because the winds are constantly coming from both directions, they will be forced to rise up. What do you think? What will be the eventuality? It will rise up. Very simple. Again, thank you for not saying it reaches A. So here, it rises up. So here, the winds, when they are colliding in this region, it will have no other path to go. Where will it go? It will rise up. It rises up. It reaches up till the level of tropopause. After reaching tropopause, where will this wind go? Again, the same fundamental at play. It cannot blast through and go to the next floor. So it will simply diverge again. Right? Now, in this, there are creations of wind circulation, and there is creation of a high pressure, low pressure system as well. But none of those high pressure or low pressure systems which have been formed, at no point have we taken the factor of temperature into consideration at all. So here, if you think about what are the pressures created? For example, if I ask you, what will be the pressure exerted or observed at A? At A, we are experiencing that the air is falling down from above. It is sinking down and hitting the ground. So, what will be the pressure experienced? High pressure or low pressure? Always high pressure. So, here you will experience high pressure. And what about this region? B. Here you have convergence and then the air rises up. So what about the ground surface? The air is rising from the ground surface. What will be the pressure experienced? It will be low pressure. Beautiful. Low pressure. So in this, the rising air column or the sinking air column, that creates a low pressure and high pressure. But this rising air column or the sinking air column is not controlled by temperature. It is controlled by the movement of wind, either in the upper atmosphere or near the ground surface. So that kind of pressure zones which are created, which are independent of temperature realities near the ground surface, they are dynamic pressure zones. So these are pressure zones created on the ground surface due to movement of wind and is independent independent of the ground temperature. It is independent of the temperature observed on the ground. Had it been dependent on the temperature, the low pressure and high pressure, we could have called it the thermal pressure zones. But this is independent. This is not driven by temperature realities of the ground surface. Here, the simple logic which is followed is that converging air collides and rises up. Always, wherever you have two winds which are converging, they will collide and rise up. And this creates what conditions? Conditions of low pressure. Then you have diverging air or simply sinking air diverges. And this creates what? Conditions of high pressure. So like this, you have the creation of high pressure and low pressure either due to the factor of temperature or induced due to the dynamic movement of the air. Any of these can induce either of the thermal or dynamic pressure zones. Then we come to the portion of isobars, something which is quite akin to what we have studied under isotherms. Now, we had seen that if you want to study the temperature distribution across the planet, you study it by joining the places with an imaginary line where all the places exhibiting the similar temperature will lie on that line. That is what we called as isotherm. Similarly, isobars are those imaginary lines which will join places exhibiting equal pressure, right? So isobar, it is a line on the map connecting points having same atmospheric pressure at a given time or on an average, whether you are calculating the average isobar represented or a daily isobar or an hourly isobaric representation, any point of time, it will always join places exhibiting same pressure. Now, for example, A, B, C, D, and let's consider E as well. So let's say A has got 990 millibar, E has also got 990 millibar. Suppose B has got 970 millibar, C has again got 990 millibar, and D has also got 990 millibar. So all the places which indicate equal pressure, they will be joined by the imaginary line. And that will be your isobar. Isobar representing 990 millibar. So all the places which lie on this isobar, they will have 990 millibar. Only then you can draw that imaginary line. Now, let me ask you a question. And I will give you the option of poles as well. Question is, can the isobars and isotherms cross each other? I'll give you a 15-second time window. Let me know. Good. Very good. That is why I had asked the question. So, majority of you have given the incorrect answer. So, all those who have given the incorrect answer, all those who have said that yes, the answer, by the way, is B. Never. Why do I say so? Why is it that the isobars cannot cross each other? Let's suppose I have another isobar which I draw for a place, let's say F, representing 970 millibar. Now, if I were to draw the isobar here, B and F, isobars are crossing, but can this be a reality? No. Why? Because analyze this portion, this place X. Now, this place X, ideally, it lies on the isobar 1 as well and isobar 2 as well. Isobar 1 represents a pressure of 990 millibar. Isobar 2 represents a pressure of 970 millibar. So what is the pressure at X? X in that case will exhibit two different pressure. Similarly, with the case of isotherm as well, let's suppose you have an isotherm of 20 degrees Celsius isotherm, and then that is crisscrossed by an isotherm which is 10 degrees Celsius. Now, in that case, if you consider this portion X, X is lying on 20 degrees C isotherm as well, 10 degrees C isotherm as well. But any place at any point of time, it will have only one temperature. It will have only one pressure condition. It is not as if that presently, Bangalore is such a special place and people are so nice. The food is also so nice. So Bangalore at one point of time can experience 990 millibar also, 1013 millibar also, and 1100 millibar also. Can that be a reality? Absolutely not. There will be one unit or one measure of atmospheric pressure which you will experience in a place. So in this case also, X, will it experience 10 degrees Celsius or will it experience 20 degrees Celsius? So that is why you will never have the condition of an isobar or an isotherm crossing each other. Always understand that. Where do they intersect, my dear friend? Okay. Okay. So all those who have basically misunderstood the question because of the written portion, I hope you understand that the question was that can the isobars they crisscross each other, and can the isotherms crisscross each other? So I hope that is something which is clear, that the isobars cannot intersect each other, isotherms cannot intersect each other. Okay. Now we come to the portion of pressure gradient. So let me specify it so that no one amongst you later okay, we had provided the pulse, it was for 15 seconds. Now we come to what is referred to as pressure gradient. Gradient indicates what? Always indicates a difference. So when we talk about pressure gradient, it basically indicates the difference in pressure experienced. So the change in pressure with horizontal distance, that is termed as pressure gradient. Okay, so if let's say we consider two places, A and B, right? Let's consider the distance between them is 50 kilometers. And then we again consider places C and D, again at a distance of 50 kilometers. Right. Now here in the case of A and B, both of them are at the same distance. A, let's say, has a pressure of 1010 millibar. B, let's say, has a pressure of 970 millibar. C has 1020 and 990 millibar. Now, in both the cases, as you move from A to B or from C to D, there is a decrease in pressure in both the cases. In both the cases, the trend is same. That is, pressure decreases. Pressure decreases. In this case, also that is the same thing. There is a decrease of pressure. There's a difference in pressure between C and D as well. Now, where can we say that the pressure gradient is more? Out of these two scenarios, where is it that we can say that the pressure gradient is more? A to B, or in the case of C to D? Beautiful. Very simple. Oh, is it? Hmm. But nonetheless, majority of you have said it correct. It is in the first case, A to B, where the gradient is more. Why? Because in this region, the pressure is reducing by how much? It is reducing by 40 millibar. What about this one? The second case, C to D. What is the change in pressure which is happening? It is around 30 millibar. So in the same distance, where is it that the pressure is changing quickly? It is A to B. So gradient is more in 1 as pressure changes more rapidly. So that is something which is referred to as pressure gradient. Now we do know that difference in pressure, wherever you have a difference in pressure, that can always induce a movement of the wind. We know that. Earlier also we have seen that in the region of high pressure, there is surplus wind which is present. Or take a look at this image. Here you will find that in the region of high pressure, there is a surplus of particles. In the region of low pressure, there is a deficiency of particles. Always the wind will be moving from the region of surplus to the region of deficiency. That is from high pressure to low pressure. So pressure difference drives the movement of air. We can easily conclude that. Let us conclude that. So pressure difference initiates wind motion, initiates the wind movement. Always. Now, can we say that greater the difference of pressure, greater will be the velocity of wind movement? How? Greater the difference in pressure means what? In one area the high pressure is very intense, or in other area the low pressure is very extensive. So in either case, in one area you will have surplus abundance of materials, and in other area maybe an exponential deficiency of materials. So it will always drive greater movement of particles. As that difference is exaggerated, there will be greater movement of particles. Just in the case of water, if you allow the movement of water for this height gradient, water will move slowly. Increase the height difference, it will move faster. Increase the height difference, move faster. Increase the height difference further, water will tend to move faster. Similarly, if the pressure difference is 10 millibar, it will initiate a movement of air. Let's say the pressure difference is 20 millibar, it will induce a faster movement. Let's say the pressure difference is 40 millibar, 100 millibar, it will induce a faster movement, isn't it? So we can say that greater pressure difference means greater wind movement, greater wind movement. We can say that easily. So this is what translates into pressure gradient. Pressure gradient. Now, pressure gradient is directly proportional, or in other words, we can have the opposite of it. Wind movement is directly proportional to pressure gradient, or the difference in pressure. So, in any place, if the pressure gradient suddenly becomes higher, suddenly overnight, let's say that tonight something has happened, so in the region of Arabian Sea, as compared to the land area, the pressure gradient has suddenly intensified, it has become much higher. What will happen to the wind? Will the wind stop moving? Will the wind say that this is not fair, you have changed the pressure, now I am going to Delhi, I will not come to Arabian Sea? Will the wind slow down, or will the wind movement speed up? What do you think will happen due to increase of pressure gradient? Very good. It will always speed up. So that is where pressure gradient determines wind movement. If there is no pressure difference, why will the air move in the first place? As soon as there is a pressure gradient created, difference in pressure created, particles, they start to move. It is as if there is a force which they are feeling, that is why they are moving. But what is this force? It is the difference of pressure. So that is what is referred to as that force which initiates the wind movement due to difference in pressure. That is what is referred to as the pressure gradient force, or simply put, PGF. That is The force which is induced in the air, where they tend to move from a region of high pressure to a region of low pressure, from high to a region of low. So that is induced due to the difference in pressure, and that is what is referred to as pressure gradient force. Okay? No, you cannot say that wind is pressure gradient force. Wind is generated due to pressure gradient force. Okay? Kiran, see, isobars and isotherms. Isotherms will represent temperature, will be represented by degree Celsius. Isobars will be represented by degree Fahrenheit, or rather, isobars will be represented by millibar of pressure. Okay. Now we move on to the other factors affecting the velocity and the direction of the wind. Because yesterday also, while we were initiating the discussion for wind movement and so on, we had basically analyzed that whenever we stand up on the roof, on the terrace, or on our balcony, or even outside, you do experience different kinds of winds on your face. Sometimes the wind is very strong, sometimes it is particularly weak, sometimes the direction is maybe from north, maybe from south, but the other time it might be from east, it might be from west. So not only does the direction of the wind keep on changing, at the same time, the velocity of the wind is also liable to change. When you go to the coastal area, experience the wind movement. It is very strong. And conversely, if you are standing in the middle of the buildings, you will barely be able to feel any kind of wind movement at all. So, what are the factors which are at play for influencing the wind motion? So, broadly, there are three main factors, right? Three main factors: the pressure gradient force that initiates the wind movement in the first place. Then you have the frictional force, due to which the wind speed is altered or is affected because of the resistance which is offered by the trees, the buildings, etc., as the wind moves. That is the frictional force. There is another force which acts due to rotation of planet on its axis, and that is the Coriolis force. All these three forces acting together, that bring about a difference in the wind movement, that bring about a difference in the direction of the wind. At the same time, you have to understand that force of gravitation is ever persistent, it is ever present, and that is something which keeps the wind, in other words, grounded. That is something which ensures greater horizontal movement of the wind. Now, wind will always move between what? Always, wherever the wind is moving, wherever the wind is blowing, wind will always be moving from a region of high pressure to a region of low pressure. Never will you come across a scenario that a wind has been initiated at low pressure and moving to high pressure. No. Wind always blows from a high to a low. Remember that, always. Now, let us analyze all these three forces. What is the pressure gradient force? What is the Coriolis force? And what is the frictional force? And how the wind is impacted by that. So, we start with the pressure gradient force. Now, pressure gradient force is induced due to what? Due to the difference in pressure. We can always say that this is initiated due to difference in pressure, right? And whenever you have a pressure gradient force which is induced, it will always lead to or initiate the wind motion, isn't it? The most important factor for wind to be moving anywhere, at any place, the most important factor is only one: difference in pressure. All the other factors will come into play and alter the wind movement, etc. But the prime root cause why there is a wind motion, that is always going to be difference in pressure. So this difference that initiates initiates wind movement. Now, how is that difference in pressure created, by the way? Difference in pressure can be created either due to thermal factors, heating by the sun, cooling by the night, warming by the day. Thermal factor. It can be induced due to dynamic factor, movement of the wind, right? So you can have that difference in pressure created by multiple factors. So always remember that the rate of change of pressure with respect to distance is pressure gradient at the same elevation that we have seen. Wind will always blow from a high to a low. Okay. Now, isobars, they give us an idea about how the pressure is distributed. So, if the isobars are far away from each other, we can say that the pressure is changing slowly. That is why with greater distance, isobars are placed. On the other hand, if in a region the isobars, each representing different pressure, if they are very, very close to each other, means the pressure is changing rapidly. So here, when the isobars are far apart, pressure is changing gradually and slowly. If they are very close apart, that means in shorter distance, the pressure is changing. So with that, let us understand the movement of wind due to the pressure gradient. So let us understand movement of wind or pressure gradient and movement of wind. So this is the map of North America, more particularly United States. And here you will observe the presence of various different isobars. Isobars indicate the distribution of pressure. Each isobars, as you can see, will have a number indicating the pressure exhibited or experienced across that region where the isobar has been drawn. So here you have a high pressure, pressure of 1036 millibar. Here you have the ultimate low pressure, 988 millibar. So there's a pressure gradient, isn't it? What is the pressure gradient in this case? If I were to ask you, okay, let me ask you, what is the pressure gradient between high pressure and low pressure here? Let me see whether you are preparing for your CSAT or not. Pranay, incorrect. Now it is correct. Good. So pressure gradient here is 48 millibar, right? Between high pressure and low pressure, the difference is 48 millibar. So there is a significant pressure gradient which is present. But that pressure gradient is not uniform from high pressure to low pressure. In the initial stages, you observe there's a shallow gradient. Why? Because the isobars are far away from each other, which tells you, for example, in this large distance, the pressure has reduced to 1028 millibar. That is only by a factor of 10. So in that large distance, the pressure has reduced only by 10 millibar. But if you consider here, from here, let's suppose, to here, in that short distance, it has reduced by almost 20 millibar. So that means there's a steep gradient of pressure. So when the pressure gradient is steep, means pressure is changing rapidly, right? So what do we mean by that steep gradient? So whenever you have that steep gradient, means pressure is changing rapidly. Is changing rapidly. Whereas shallow gradient means what? Pressure is changing slowly. We have seen that over this large distance, the pressure has changed by only 10, whereas here in this small distance, it has changed by almost 20. So there's a higher pressure gradient. So there, in this case, you will have faster winds. And in this case, you will have slower winds. So that is why sometimes when you step out and you experience a very light, pleasant breeze, that means there is not much of a pressure gradient which is available. Sometimes when you step out and there's a very high velocity wind, that means there must be a low pressure nearby, an active low pressure where all the winds are rushing from. If you experience sometime that the wind is coming and striking your face directly, that means somewhere behind you there must be a low pressure. If you experience that the wind is coming from behind you, means somewhere ahead of you there is a low pressure where the wind is trying to reach. So that is how pressure gradient initiates the wind motion in the first place. Then we come to another factor, that is the Coriolis force. Now, Coriolis force is an apparent force. We say it is an apparent force because this is a force induced completely due to rotation of planet Earth. If the planet would not be rotating, Coriolis force would be absent. So this is something induced due to rotation only. Now, because of this rotation, it creates a scenario where any moving object which is not fixed to the ground, any moving object like you have ocean currents, like you have airplanes, like you have winds, these are not fixed to the ground, is it? So any of these which have an independent movement independent from the ground, they will experience a deflection or a deviation. Objects moving in the northern hemisphere will deflect to their right. Objects moving in the southern hemisphere, they will deflect to their left. What that means is, for example, here an object ideally would be moving straight forward, but then because of the rotation, it will experience a deflection rightwards. Similarly, in the southern hemisphere, ideally it would be moving southwards, but because of a deflection or because of the rotation of the planet, it starts deflecting leftwards. Okay, so before we go into the intricacies and the depth of it, first of all, the basics, so that you don't tell later that basics is weaker. So when I say basics, I will start with the very basics of what do we mean by right and what do we mean by left. So here, when we say a wind is moving like this, yes, that is why. Okay. When we say the wind is moving like this and there is a deflection either here or here, I name it as 1, I name it as 2. I will launch a poll. I will give you 15 seconds for it. Which amongst them is considered to be left? Out of 1 and 2, which is considered to be left? Good. So most of you have given the correct answer. This is the left, right? And this is the right portion. Okay. So how is it that we determine whether the wind or river, anything, how do we determine their left and the right portion? Does it depend on from what angle are we looking at? No. Whenever you have to determine that kind of a deviation, always look at it, get your point of view from here. Okay, this is your point of view. Look in the direction where the wind is moving. Imagine that you are looking in the same direction where the wind is moving. Your left or your right will be the rightward deviation. Your left will be the leftward deviation. Always you have to imagine that you are standing in the same direction as the direction of the movement of the wind. So if the wind is moving, let's say like this, you have to imagine yourself standing here and looking in the direction of the movement. So your left will be the leftward deviation, your right will be the rightward deviation of the wind. Always keep that in mind. Okay, now why is it that this Coriolis force is induced? Purely because of rotation. So, if ideally I were to create a planet or a scenario in a planet where ideally, let's suppose this is a planet which does not rotate at all, which is still, it does not rotate. So, in that case, if the objects were to travel like this, they would have reached their location without any deviation. Okay, if it is not rotating. But the moment it starts its rotation, as you observe in the case of planet Earth, there is a kind of a deviation here. It will indicate a deviation due to the rotation. That deviation which is induced, it is referred to as the Coriolis effect, or the force is referred to as the Coriolis force. Now, while there are significant concepts in place, even for the derivation of it, you have the conservation of angular momentum which happens due to rotation. So that is why there is a kind of a deviation. We will not dip our beaks into such detailed scientific explanation of it. I'm sure by the time that we are done with the scientific explanation, most of you will start reconsidering that why I have chosen civil services. I was so happy reading easier things. So I will not take you there. Let me very briefly and simply tell you why this happens, if at all. So this happens because of initiated due to different rotational speeds observed in different latitudes. Remember the first session if you can. In the first session, we had seen this, we had talked about this, that different places on the planet, they experience different speed of rotation. Even though the entire part is a solid object, blah, 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 and all of them will not break, etc. But still, when you have an area around the equator, when this is also rotating, and it is managing a very large distance, a distance equivalent to the circumference of the planet in one rotation, and one rotation happens in how much time? One day, 24 hours. And if you consider this particular portion near the Arctic, in one day, what is it doing? Covering this area in one day, right? This portion at the poles, almost not moving at all. So, all these places, in one day, they are covering different distances. So, that is why we can say that the speed also that they will indicate will be very different, right? So, the key to Coriolis effect lies in the Earth's rotation. Specifically, Earth rotates faster at the equator than it does at the region of the poles. Why? Because Earth is wider at the equator. So, to make a rotation in the 24-hour period, equatorial regions race nearly 1600 kilometers. So, in one rotation for one day around the region of equator, there is a coverage of almost 1600 kilometers. Whereas near the poles, there is almost zero movement at all. 1600 kilometers per hour is the speed of rotation at equator, whereas at the region of the poles, it is 0 kilometer per hour. So velocity of rotation is maximum at the region of equator, and speed of rotation decreases as one moves towards the poles, with the speed becoming almost zero at the poles. Let us write this. So speed of rotation is maximum where at equator, decreases towards poles, and is zero at poles. Right? So, if I consider this place A and if I consider this place as B, both of them rotating, they will take 1 day to complete one rotation. But we can say that velocity at A will be very high as compared to velocity at B. Velocity at A will be much higher than velocity experienced at B. We can say that, right? Velocity at poles will be zero. Now, if I am throwing an object from a region which has a higher velocity, that is A, to a region which has got lower velocity, that is B, how can the object reach there straight forward? If there would have been no rotation, each of these places would not have indicated any movement at all. So the things would have moved without deviation, but they are moving at different speeds. So it is because of the difference in speed that a bending is induced. Always remember that. It is because of the difference in speed, difference in speed induces the deflection. Now, for your general studies, even this portion is more than sufficient. For general studies, in fact, even if you just know that in the northern hemisphere it bends to the left, it bends to the right, and in southern it bends to the left, even that is more than sufficient. Having said that, we'll try to understand it with the help of analogy of speed difference. What happens when there is a speed difference? That is something we are going to analyze with the help of the very famous car example. So here we'll take the case of what happens. Why is it that if objects move from one place exhibiting a different speed to another place exhibiting another speed, why is it that there will be any deviation, if at all? So for that, let us imagine three cases. In all these three cases, let us imagine there are two vehicles, cars. Okay? In all of them. Now, in the first case, let us name this as car A, B. In the first case, let us assume both car A and B, they are moving at the same velocity, same speed of, let's say, 30 kilometer per hour. Both of them. Now, someone sitting in A has got a ping pong ball. Imagine that you are traveling on road and another vehicle driven by your friend, he's or she's also driving at the same speed. Now you are, if you compare each other, so from your point of view, that vehicle appears to be almost static, right? Because you are able to see everything which is going on in the vehicle, whatever is happening in the vehicle. On the other hand, if some vehicle simply rushes past you, you might not even be able to figure out who is sitting in that vehicle. But when two vehicles are moving at the same speed with respect to each other, you guys have a kind of a similarity, a kind of a relative staticity which is present. They are stable. So if some individual from A That person throws a ball to an individual sitting in car B. Relatively, both of you are static because you are moving at the same speed. So that ball which is thrown will easily be caught, right? So in that case, because they are moving at same speed, the ball has been caught. What about the second case? In second case, let us assume that A is moving at a speed of, let's say, 70 kilometer per hour. Okay. And in this case, let's say it is 20 kilometer per hour. Yes, Priyanka, that would be correct. So here you would have A and B which are moving, right? Now A and B both are moving at a very different speed. Now at this speed, if someone who is sitting in A decides to throw a ball at someone who is sitting in B, now what will happen? By the time that the ball is thrown and by the time that the ball travels, will it be able to reach B? No, B will be very far behind. The ball will fall somewhere ahead, isn't it? Because when you are throwing something from an object moving at a faster speed, things have a velocity that they gain. So this will basically fall where? If I ask you that the object or the ball which is thrown from A, will it be received at B? Will it be received ahead of B? Or will it fall behind B? What do you think? Very good. It is something which will fall ahead of B. Why? Because A is moving at a much faster speed. So when A reaches here, that is when someone throws the ball. So obviously that ball will also have a relative motion. It will fall somewhere here, isn't it? Those of you who are getting confused about ahead or behind, think about it. Suppose you are an individual standing here on a railway platform, right? You have a bag of chips in your hand and you are standing there. Now, in front of you on the platform, a train is moving. A train is moving which has got no stoppage in the platform that you are standing on, right? And you know, there is one individual who you know, your friend is traveling through the train. You have talked on the phone that, okay, when you see me, you throw me the gift packet that you have to give me, I will catch it up and go away. Train is moving at a speed of 20 or 40 kilometer per hour. That your friend is carrying a special gift packet for you, that you are supposed to receive. Now that individual sees you when the bogie reaches there, and that individual then throws the item. Will the item be directly caught by you? Will, by some miracle, as the train is moving in this direction, you are standing here, by some miracle the object will fall behind, or will the object fall ahead? Always the object which will be thrown will always fall ahead. It will be scattered, it will be mangled, it will be destroyed, but it will fall ahead, right? Can you think of any circumstance where someone throwing something from a moving train has a thing which falls behind the platform? No, it will always fall ahead, isn't it? So that is how, when you have an object which is thrown from a faster particle, it will always tend to fall ahead, right? So if you have to try it out by a more physical example, by a more personal level, don't follow my saying in that person has led me to do this. But if you seek real adventure in your life and you still are not able to understand this, ever if you have tried to jump from a kind of a slow moving bus, you feel that you will get down here, but by the time that you get down, you maybe tumble ahead somewhere, you fall ahead somewhere. It is not going to be the case that if I have to get down here and the bus is moving in this direction, I'll jump, I will fall behind. That will never happen, right? So that is why when the objects, they are moving from a faster speed to a slower speed, the object tends to fall ahead. Okay? When an object moves from a faster speed to a slower speed, it falls ahead. We can say that. On the other hand, let us consider another example. In this case, let us consider that A is moving at 40 kilometer per hour, and this time B is moving at 110 kilometer per hour. Right? Now, here the individual is sitting with that tennis ball that I have to throw. When B comes near me, then I will throw. So B comes parallel to A, and then B overtakes because B is moving at a much greater speed, right? So when the ball is thrown, now, will the ball be caught by B? Will the ball fall ahead, or will the ball fall behind B? What do you think? What will happen? Obviously, it is going to fall behind. How? Because by the time the ball will reach where B is, B would have moved somewhere here, right? B would have moved somewhere else. So that is why when an object moves from a slower speed to a faster speed, it falls behind. So when an object moves from slower speed to faster speed, it falls behind. What about the first case? The object is moving in the area of the same speed, so it will be caught. There is no deviation, right? So when moving between same speeds, no deviation is observed. No deviation is observed and the object is caught easily, right? So based on these three factors, we can analyze the entire aspect of the Coriolis effect. How? Let us take a look at that. So when we talk about the planet Earth is not a sphere. It has got a unique shape where it is flatter at the poles and bulged at the region of equator, right? At the region of equator, there is a slighter bulging. So this is a unique shape of the planet Earth, and we call this shape as a geoid. Okay? Flatter at the poles, slightly bulged at the equator. Now, here, when you think about it, where is it that it is flat? In this region. Where it is bulged? At equator. Now, this is rotating consistently west to east. That is what is giving various velocities. Now, if I give you three different places, let's consider this place. Let's consider this place as well. right? Now here, speed is, let's consider this, velocity B, velocity at A, velocity at C. Here you will have A. Here, let's say you have B. Here you have C. Okay? Now, if an object is moving from A to B, can I not say, because VA is much greater than VB, as an object is moving from A to B, can I not say it is moving from a faster speed to a region of slower speed? This case, faster speed to lower speed, because VA is greater than VB. In that case, what happens? The object falls ahead, isn't it? So in that case, the object's destination is B. But because B is moving slower, A is moving faster, the object will fall somewhere here, B dash. Right? So overall, there's a kind of a deviation which is experienced. And that deviation from the natural path is in which direction? It is in rightward direction. Hence the rightward bend. Now, what if the object is moving from A to C? Again, it is trying to move from an area of faster speed to a slower speed. Why? Because overall, the speed at equator will be much greater than the speed closer to the polar region. So again, from faster to slower, rather than C, it will drop somewhere here, C dash, isn't it? So this will be a deviation. And as compared to the normal expected path, what is the direction of this deviation? Left. So that is why objects moving in the northern hemisphere will have a bend to the right. Objects moving in the southern hemisphere will have a bend to the left. The converse of it. Let's suppose here you have an object from D trying to reach E. Okay? And let's say from F trying to reach E. Now from D to E, that is a motion where velocity of B is less than velocity of A. So that means object is moving from slower to faster. Slower to faster, the object always will fall behind. When you throw from slower object to a faster object, object always falls behind. So here it will fall behind E. Let's say somewhere here, E dash. Now that is a deviation away from the expected path in the rightward direction. Similarly, from F to E, again from slower to faster, it will again fall behind somewhere here. Again deviation on the leftward side. So the difference in speed of different places, that is what induces a bending. Difference in speed always induces bending. Now, let us consider two portions very close to equator. Two portions immediately in the vicinity of the equator. 3° north, 4° north, 5° south, in that region, let's suppose. Now here, in that immediate vicinity, let's suppose I mark this place as 1 and I mark this place as 2. So, because it is very, very close to equator, so from 1 to 2, if I consider velocity of 1 and velocity of 2, can I not say they will be approximately same? Right? We can say approximately same, because the radius in this case will be significantly similar. So if the velocity is equal, what do we observe? No deviation. So if an object is traveling in this small distance, it will observe no deviation at all. So that is why we say that at equator, here you have no deviation. And that is why we say at equator, Coriolis force is 0. Himaya, it is not the direction of movement which induces rightward leftward bend. It is whether you are in the northern hemisphere or the southern hemisphere. When you are in northern hemisphere, regardless of whether you are for direction northwards or southwards, you will have a rightward bend. When in southern hemisphere, regardless of the direction you are moving, it will have a leftward bend. So here at equator, Coriolis force is 0 because there is no change in velocity. Now, that tells us that wherever there is a rapid change in velocity, there will be significant deviation, much greater deviation. Now here, at the region of the poles, what is the speed of rotation? V at poles is 0, isn't it? It will be 0. So if I compare VB and VP, if I compare this, and if I compare the difference VA and VB, right? The difference of velocity at A and the difference of velocity at B, if I were to compare it with the difference experienced at poles and B, which difference do you think will be greater? Where is it that the difference experienced in velocity will be greater? Always in this case, VB and VP. That is where difference will be much greater. Why? Because regardless of whichever place you choose, VP is 0. So whatever there is a speed, that is the difference. So that is why, because the difference in speed of anything moving to the poles or away from the poles, the difference in speed is so significant. That is why we say Coriolis force or the deviation experienced is maximum at the region of the poles, because the difference in speed exerted is maximum. Why? Because the speed of rotation at the poles is 0. So Coriolis force deflects the winds to the right direction in the northern hemisphere and to the left in the southern hemisphere. The deflection is more when the wind velocity is comparatively higher. It is maximum at the poles and is absent at the region of equator. This Coriolis force acts perpendicular to the pressure gradient force. What do we mean by this term? It acts perpendicular to the pressure gradient force. Understand. For example, let's assume we consider northern hemisphere. In northern hemisphere, the bend will be to the right. Always. Let's consider a region of high pressure and let's consider a region of low pressure. Now, the direction of pressure gradient force, there will be a pressure gradient which will be available. This is the direction of pressure gradient force. So the wind will initiate a motion towards that, right? Now, as the wind is moving, because we are in the northern hemisphere, by the way, will the wind move straight? No, it will experience deviation. Deviation in what direction? In the rightward direction. The wind will always experience a deviation on the rightward direction, right? So here, this is the force. That is the Coriolis force. Okay? Coriolis force is acting in rightward direction. So the eventual resultant wind will be in this direction. This is the resultant wind motion. This is the resultant wind motion that you have. But what do you see? That Coriolis force is perpendicular to the pressure gradient force because it is trying to deviate the winds to the right. So that is how you have the difference in pressure. Now, if the wind speed is more, the wind will experience greater deviation. Eventually, if the wind speed is very, very high, those winds can start to move almost parallel to the latitudes. They can have a horizontal motion. Next time, when you take a look at the image of Jupiter, observe something carefully. In Jupiter, you will observe there are various bands which are there, reddish bands, whitish bands, etc., which are present. After the class, look at one of the image, very basic image from Google only, you can find that. You'll find the bands are present. What are those? Those are wind movement. And those tell you that what would be the speed of the wind, that they are moving almost horizontally. So the Coriolis force is maximum. As the wind velocity goes up, deflection is more. Eventually, it can have a movement like this. Okay? So that is the fact about Coriolis force. Okay? Third point, Coriolis force is maximum at the poles and absent at the equator. Here we had seen earlier, Pankaj, that in the region of equator, if I consider two places, 1 and 2, V1 and V2 is approximately same because the radius is almost similar in this case at 1 and 2. So because this radius is similar, speed of rotation will be similar. So an object moving between 1 and 2, they will observe no deflection. So because they are moving at same speed, no deflection means no Coriolis force. Whereas at the region of the poles, there is always going to be a difference in velocity because wherever you consider as a point of reference at poles, the speed will be zero. So always there will be a greater difference. Hence, you have greater Coriolis force as well. Okay? So that is the third point. Okay. So now explain fourth point again, and someone will say explain the second and the first point again. So we are back to square one. Okay, the last point, I will repeat it very quickly. Try to understand. Coriolis force acts perpendicular to pressure gradient force. Don't try to memorize it. Don't try to learn it. Think about it in normal scenario. When we consider the planet, let's say, when we consider two places A and B, right? Let's say B has got the high pressure. A has got the low pressure. So there is a pressure gradient force. What is the direction of pressure gradient force? This is the direction of pressure gradient force. This is the ideal movement which should have happened. But assume that we are in the northern hemisphere. So what will be the movement? Movement will be somewhat here. It will bend to the right. Isn't it? This is the resultant movement. So why is it bending to the right? Because there is a Coriolis force. Coriolis force is acting in which direction? It is acting in rightward direction. What is the rightward direction? This is the rightward direction. This is the direction in which the Coriolis force is acting. So can we not say this is perpendicular? The same logic applies here. Okay. Now we come to the final of these forces, that is the frictional force. Frictional force, simply put, is the force of resistance which is offered. In the path of the wind movement, any resistance which is offered, that is the frictional force. So in any place, for example, if you consider any particular region, you will have hills, mountains, trees, valleys, buildings, etc., forests which are present, and so on. Isn't it? So as a result of that, the wind which is going to move, the velocity of the wind is going to reduce because of the force of resistance. Conversely, if you consider a wind moving at a higher elevation of maybe 5 kilometers, 10 kilometers, will it experience the same frictional drag? No. So here, velocity will be higher. That is why velocity of winds at an altitude is always going to be greater, because near the ground surfaces you will experience that force of resistance, but higher up you won't experience that. That is why wind velocity will be higher. Now, over the water bodies, sea level, etc., there again, the force of resistance is almost negligible. There are no obstructions over the oceans. So, there again, the wind is able to gain momentum. That is why over water bodies, you experience much faster movement of wind as compared to land areas. So, this also tends to alter the speed that the wind follows or experiences in a region. Okay. So now we will come to the portion of air circulation. Before that, this is the final portion that we will do, and then we'll take a break. So here we talk about onshore and offshore winds. These are winds which have an interaction with water and land areas together. Onshore winds are the winds moving from moving from water body to land, and offshore winds move from land to water body. These are different from your land and sea breezes that you would have heard about. These are long distance winds. They move over long distances. Land and sea breeze is restricted at a distance of width of around 40-50 kilometers only. So suppose here, if you consider, let's suppose here you have a high pressure. Now, that high pressure would mean that winds move out of that high pressure. Winds will move like this. Let's suppose you have a low pressure here. So, winds will be moving towards that low pressure. So, the winds which are coming towards that low pressure, are they onshore or offshore when you consider the American coastline? Are these winds going to be onshore or offshore? What do you think? Easy. These are onshore because they are coming over to the land. Now, whenever the winds move from water over to the land, they will bring lot of moisture. They will be able to carry a lot of water vapor along with them. And those water vapor, they will drop it off on the land in the form of rainfall. So always they bring moisture, cause heavy rains. Whereas, if you consider that there is a creation of a high pressure here, there is a creation of a low pressure here. So the winds are moving in this direction. So they will be offshore. Will they be carrying any amount of water vapor along with them? No, because these winds are originating over the land. So that is where offshore winds are devoid of winds or devoid of vapor, of moisture, cause heavy, or you have lack of rainfall. Okay, so that is what you have as the reality of onshore and offshore winds. Now, Shivam, you have asked a question and you have tried to really I hope that you have understood what I'm trying to convey here about the portion of the poles, and you have really got into the nitty gritty of VA, VB, and VP. Let us take your assumption. Your assumption is that VA here is how much? 50. Your assumption is VB is 20. And your assumption obviously is that velocity at P is going to be 0. So the velocity of rotation is rotating by 30 in this and only by 20 in this large distance. Does that make sense, my dear friend? always understand why is there a Coriolis force. Even if I say that Coriolis force exists or does not exist, understand why it exists. It exists because of difference in velocity. Whenever, wherever, when the wind moves between different areas, if at all there is a difference in velocity, it will induce a deviation. Now, why it does not induce a deviation at equator or closer to the equatorial areas? That is because of the fact that as the object moves between them, it moves in areas of equal velocity. So there is no deviation. When an object moves closer to the region of the poles, there you have the polar rotational speed is zero. So even if there is a slightest of difference, that induces a deflection. And that is where you will see that the deflection is maximum. It is not for me to say. I have not had the entire wind encyclopedia in my house from the childhood days that I will show you that this is the wind I experienced when I was in Arctic, and when I went to Antarctica, the wind speed was this much. No. This is a fact which has been proven by various different scientific records, by various in other planets also. This is something which is absolutely observed. Okay, so get the larger picture. Is the larger picture clear, Shivam? Or do you need to analyze VA, VB, VP speed separately? What do you think? If there is any doubt, please ask. But I hope you understand the larger picture rather than getting entangled in the nitty gritties. Don't do that. Okay. Why offshore winds are devoid of moisture? Offshore winds are devoid of moisture, Suruf, because imagine there is a wind moving from here to here, from China to South China Sea. Now, that offshore wind, where will it pick the moisture from? It is coming from land area. So, where will it get the moisture? So, that is why it is devoid of moisture. No, Chinmay, the vapor from local water body and by trees, will not they be carried by the offshore wind? No. That is almost negligible. The vapor from where the trees, etc., the lakes that you are talking about, that is negligible. Winds, they travel all the way from here to across thousands, tens of thousands of kilometers. Then they are able to cause some rainfall in Kerala coastline. How can you expect that from 5 to 10 trees that are there, it will pick up so much moisture? It is very, very little. Okay. Can we say that onshore winds are colder and heavier? You can say that it is cold, it is heavier. Not always will it be colder. Why will it not always be colder? Imagine, Rohan, that when we are talking about, let's say, the winter season, you will have the water which is warmer, land which is colder. Can there be a motion induced? There can be, based upon dynamic pressure conditions. And there you will have warmer winds coming into colder areas. Okay. How land has much pressure than oceanic areas? It can depend. It can depend upon thermal conditions. It can depend upon dynamic conditions as well. Isobar should not be parallel with latitude. Why will it be parallel to latitude? Does the temperature change regularly with latitude uniformly? No. So why will the pressure change? Does the wind movement alter uniformly with latitude? No. Then why will it have a change? So it does not. Okay. And yes, Pooja, that is correct. Abhishek, can we use wind always? You can. Why no deflection at equator, Moina? Because very simply put, at the region around equator, because of the shape of the planet, there is a bulge created around the region of equator. So if you consider the portion 5 degree north, 5 degrees south of equator, there is almost a similar speed of rotation. So that is why when the objects move between similar speeds of rotation, there is no deviation. Okay. Winds from river or lake to water body, minimal. Yaram city, that is minimal amount of moisture. That will never empower the wind of from that much amount of moisture. Okay. Uh, Gagan, the point from where wind rises or sinks, is it point where pressure? Yes. Wind eventually rises or sinks, also creating that high pressure, low pressure. You'll get all of this very clearly. Just wait for a couple of slides. Moist air is cold. Is it a must? Not always a must, Rahul. Prithvi, if there is a place where they are experiencing cyclone or tsunami, due to this, at some other place they are experiencing rainfall. Cyclone, atmospheric phenomena; tsunami, a geological phenomena, right? So if you are listening to a kind of a statement that relates all of them and is able to relate tsunami with rainfall, catch hold of that person who is telling you this. That's all that I can say. Suraj, can't we say throw in straight, but due to where it looks like deviation? Because yes, you can say that. Okay. Okay. So let's take a break now, guys, and let's be back. It is around, let's be back by around 7:10. Devansh, not necessary. Not necessary, my dear friend. Sachin, how can we know that from where these are coming? Winds, with the help of anemometers, with the help of satellites. That is how we know. Yes, yes. Isotherms and isobars can cross each other. Difference in wind velocity determines Coriolis force. Pranay, yes, that determines. How do we measure wind? We measure wind with the help of an anemometer and a wind vane. Wind vane points you to the direction in which the wind is blowing. Anemometer is like four discs of sorts which are present at the central hinge, and their rotation gives you the wind speed. Okay. Rain will only happen in low pressure, Rohan. That is correct. See, Moina, the Coriolis force is not because of the absolute speed. It is because of the difference in speed. From one place to another, what is the difference in speed which is experienced? So, from one point at equator to another point immediately above equator, will you experience a difference in speed? The answer is no. From equator, if you are trying to move, let's suppose this is the equator. If you are trying to move here, yes, there is a difference in speed. Yes, you will experience deviation. If from here you are going to equator, obviously there is going to be deviation. Obviously there is a Coriolis force. But at equator, when we say the Coriolis force is zero, in between here, do you experience a deviation? No, because the speed is similar. So at this point, the deviation is zero. Okay. A confirmation regarding the audio, please, if you're able to hear me out. Thank you. Now, we come to the portion of air circulation or circulation of air, which happens and which is observed across the planet. Now, the prime question which we receive or we have in our mind is, why is it that the air circulation will be observed across the planet? The reason is very simple. When we have the planet as a spherical object, and basically you have solar rays which fall upon them, now the intensity of sunlight which is received at different places of the planet, that intensity of sunlight will never be the same. You will have the region around the equator and the lower latitudes, they will be experiencing more direct rays of the sun. These areas, they will be experiencing more direct rays of the sun. Whereas these areas, that is the polar region, they will experience a slanting rays of the sun. So can we not say that heating by the sun causes differential heating in different parts? We can always say that, isn't it? Now, different parts will have, or different regions, just a moment. Okay. So, apologies for the interruption. And there is a question which has been asked. VD, my dear friend, you have asked a question that will Coriolis force exist in atmosphere or at the surface of the earth? Any object which is free to move, any object which does not stick to the ground. So for example, if you are running on the ground, you will not experience Coriolis force. If you are moving with your vehicle, you will not experience Coriolis force because you are sticking to the ground. If on the other way, you might end up innovating or inventing a new device which allows you to fly from, let's say, Bangalore to Delhi. And if you're flying, you will experience that deflection because you are not stuck to the ground. Okay. And again, a request with folded hands for all of you. Please understand, myself and the team included, we are trying our level best to get your queries resolved. That is why we are here. That is the sole purpose why we are here, why we are trying to put in newer ideas and trying to solve those ideas. The prime purpose here, guys, is to help you understand. I'm not going to appear for the civil services, neither the subject matter experts are going to appear for the civil services. But then, even when you talk to the subject matter experts, please have a decorum that you maintain. That is an absolute must. Okay. If you are not following a pre-required set of decorum, that does not suit well for an individual who is aspiring to be a civil services aspirant. Have you ever come across any successful candidate who is not well spoken, who is not well mannered? And this is something which is very easily distinguishable when you have a face to face interaction, even with the interview board. So kindly have that level of decorum. All the subject matter experts that you are interacting with, all of them have appeared for multiple interviews, I'm saying. So all of them are much more accomplished than what you might estimate or you think about. So please, all I'm asking for, have a level of patience when you are asking a question. Your question will be answered too. If not immediately, after some time, the SMEs will get back to you. If still the question is not solved, write to us at IS Live. You can write a mail personally to me as well. We will get back to you. Okay, so there is no reason why you should be losing patience and why you should be resorting to maybe harassing someone. So please don't do that. Okay, I hope that is clear. And so that is why few of the questions, if it is not replied to immediately, no reason for you guys to lose your bearings and lose your patience. Okay, yes, Arindam. Then another question I'll answer, that is Ranjan. Do isotherms and isobars cross each other? So isotherms within themselves, you will not have two isotherms crossing each other. Within themselves, you will not have two isobars crossing each other. But an isobar can always end up crossing an isotherm because both represent different factors which is present. Okay. So this is something which has been pointed out to me right now. So that is why I'm picking it up as an issue. Next time, when it is found out that someone is misbehaving with their words, either with the SME or in the class, it will not be taken very kindly. So kindly try to make it up. Try to have a larger gaining of an idea, my dear friends. You are here not because you want to be a meteorologist in your life. You are here because you want to clear civil services examination. Keep that goal in front of you. Rest everything. Whatever I say, whatever someone else says, that is an externality. Keep your mind to the goal and work on it. Okay. Now, here, when we talk about the differential heating which is caused or which is created at different places, that differential heating, that will induce different pressure zones as well. That means in certain area there will be a lot of heat, in certain area there will be a lot of cooler conditions which shall be present, isn't it? Now that would mean that, let's say, in the region around equator, we always have a kind of a heat surplus. Whereas in the region of the poles, why do we have a heat surplus here? Because we receive direct rays of the sun, direct vertical rays of the sun. Whereas in the polar area, you receive slanting rays of the sun. So that will always have a kind of a heat deficit. Isn't it? So if the conditions were to prevail just like this, the scenario would be that the region of equator would have continued to gain the temperature year after year and might reach boiling point. Whereas the region at the poles, there the cooling would have happened year after year and it would have been extraordinarily cold. But that does not happen, because wherever there is that differential heating, there will be movement of wind, movement of ocean water, and that carries out distribution of heat. So with the help of wind and oceanic movement or oceanic circulation, the wind, or rather the heat, is distributed across the planet. Oceanic circulation, basically the ocean currents, etc., which are in presence, we will study about them in significantly greater detail when we come to oceanography. But as of now, let's assume we don't know anything about oceanic circulation, because we have not even talked about it till now. So let's assume that there is something happening in the ocean. Along with that, the air movement that is responsible for that distribution of heat, which happens from one region to another region. Heat surplus means that this is an area which receives extraordinary amount of heat, and every day it receives more amount of heat. So that is why there is a heat surplus in that region. Now, it was in the 1700s when you had the first atmospheric circulation model, which was postulated by Hadley. approximately around 1730s, was when Hadley postulated the first atmospheric circulation model. And that was referred to as the unicellular model of circulation. Unicellular model of circulation. Now, this unicellular model of circulation, this was provided by Hadley. Now, what is this? So, Hadley, he basically had the idea that, look, temperature is the main contributing factor to influencing pressure. He had the idea that wherever the surface is warmer, the air above it will also be warmer. And by that, he postulated this model of circulation. What is that? That is, if I consider the planet and I consider places at equator, that is 0 degree, I consider 90 degree north, that is the North Pole, I consider 90 degrees south, that is the South Pole. Now, Hadley said that, look, equator receives lot of heat. So when equator receives lot of heat, so this land will be warm. This land will be warm. When this land is warmer, so the air which is directly in contact with this land, that will also get warmer. So this has got warm air. Warm air. Right? Now, when air gets warmer, it tends to become lighter because the particles, they will have more energy. They will start escaping the system. So it becomes lighter. And when it becomes lighter, it starts to climb. It starts to rise. It will rise up till where? Up till the region. Up till where will it rise? Will it rise up till tropopause, stratosphere, stratopause, mesopause, or even thermosphere? Where do you think the wind will rise up till? Beautiful. Up till tropopause. That is where the upper ceiling will start acting. That is tropopause here. Now, as the wind is able to hit the tropopause, it will diverge, it will deviate, portion going towards both the poles. In the region of the poles, what do we have? We have very low temperature, very cold conditions. Temperature might be minus 30, minus 40 degrees Celsius, minus 50 degrees Celsius. Now, in this cold condition, what will happen to the air? The air will also become cold. Now, colder air has got a tendency to sink. The colder air will sink. It will hit the base here. Cold air will sink here. And where will it go? It will go to a region where you have low pressure. Where is it that you have low pressure? Here you have the persistence of a low pressure because there's a rising air, isn't it? So the wind, which is sinking at both the poles, they will be attracted towards that low pressure. Here you have extreme high pressure. Extreme high pressure. In this case also, extreme high pressure. So naturally, the wind will be moving towards the region of low pressure, and that will be able to complete a kind of a convection current in each hemisphere. So overall, in one hemisphere, how many circulations you have? In each hemisphere, you have one circulation. That is why it was referred to as unicellular. Uni means one. That is why unicellular model of circulation. It talked about the rising air at the region of equator and sinking air at the region of the poles. But then later on, that is in the 1800s, you had the American astronomer and meteorologist at the same time with the name William Farrell. Now, William Farrell observed something very unique. And for William Farrell, it was very simple that this model can never be in existence. This kind of a circulation can never be in existence. Why? Because William Farrell maintained, and William Farrell had the idea of Coriolis force, which which Hadley never put to use. So William Farrell maintained that, look, in the upper atmosphere, you are saying that winds from the equator, they are moving, and they are moving peacefully, and they will move all the way till the region of the poles. You are saying that despite the rotation of the planet, that is how disciplined the winds are. Won't there be a deviation in the form of Coriolis force here? There will be. And you are saying that on the surface, the winds are going to move from from the poles all the way to the equator. So William Farrell said that, look, how can it be possible that the wind is moving tens of thousands of kilometers to reach the region of equator? It will experience so much of resistance by that point of time, it will not be able to reach there. And nonetheless, you are counting out the portion of Coriolis force here. You are not even accounting for the Coriolis bending. So how can it happen? So based on that, in the 1800s and the late 1800s, this unicellular model of circulation, this was discarded. And then came what we refer to as tricellular model of circulation. Tricellular model of circulation. Model of circulation. Now, earlier one was referred to as unicellular because in each hemisphere you had one cell. This is referred to as tricellular. That means in each hemisphere you will have 3 cells of circulation. Why will there be 3 cells of circulation? Just to show you a glimpse of how it looks, this is how the new circulation pattern looks like. Let us understand how this can come into existence and why. Why and how, let us address these basic factors. So let us assume this is 0 degree. Let us assume this is 90° north. Let us assume this is 60° north. And this is 30° north. Not exactly this. Okay, I'll give you a kind of a range so that it is not confusing. Why only 30°? Why only 60°? Let us assume 50° north to around 60° north. We consider that region. 25° north to 35° north. Let's consider that region. Okay. Now, here, let us consider how is it that air circulation happens, or what results as a consequence of the air circulation, where it begins, where it ends. So here, when we talk about the region of 0°, this is the region of lower latitude, will receive direct heat from the sun, vertical heating. So as a consequence of it, due to heating, the air will also get heated up. So the air will start to rise after getting heated up. Now this rising air creates what conditions on the ground surface? It will create a low pressure on the ground surface. But we'll come to all the pressures later on as well. Another pressure that I want you to think about is the pressure exerted at the poles. Now at the region of the poles, because the temperature will be perpetually very low, it will always be very cold. So there also the air will become heavier and will have a natural propensity or a natural tendency to sink. Right? So that will create a thermal high pressure here, a thermal low pressure at equator, and a thermal high pressure at the region of the poles. This in itself is capable of inducing multiple circulations. Let us understand how. So here, when we have the air which is rising up, yes, Nitesh, perfect. When we have the air rising up, as it rises up, it slowly and gradually becomes cooler and gives its heat to the surrounding environment. It continues to rise up. It becomes cooler along the way as it rises up. Eventually, it will hit the ceiling in the form of tropopause. When it hits the tropopause, that is when the winds will diverge. One goes towards the southern hemisphere, other one comes towards the northern hemisphere. Now, this upper altitude wind, that is the wind moving in the region of tropopause that you are seeing. Listen to this carefully. This upper altitude wind, will it experience Coriolis force or not? What do you think? Will this wind experience Coriolis force or not? This wind that I'm talking about. Perfect. It will experience, as it moves away from equator towards the poles, it will experience Coriolis force, right? So as it starts to move, that is when it is going to experience Coriolis force. At the region of equator, understood that Coriolis force is zero. But as they initiate their motion towards the poles, it will experience a Coriolis force, isn't it? Now, how will that look like? How will that look like? Let us think about only representing the upper air movement. Upper air movement. Here, let's assume this is the equator, 0 degree. Now the wind has risen up in this portion around the region of equator. Let us consider the portion which is moving north. It is moving north in the northern hemisphere. It will experience a rightward deviation, a rightward deflection because it is in northern hemisphere. So the winds in upper air, they will experience a rightward deviation. Eventually, they will bend to such an extent, you can see that further the wind's northward motion is not possible. More winds will rise up, more winds will accumulate themselves in this area, isn't it? So, surplus wind accumulation. So that means as the wind is coming here around 30 degrees, 25, 30 degrees north and 25, 30 degrees south, there is a surplus addition and accumulation of wind. Also, remember that all the meanwhile, as the wind is spending some time in the upper atmosphere, it is getting colder by the day. And it is becoming colder and colder. Eventually, not only is there a significant accumulation, but also because of cold conditions, the air in this region, in this area, the entire area, the air is going to become denser and colder as well. So, what will happen to the air here? The air will start to sink. You have a sinking air. Now, this sinking air has got absolutely nothing to do with the ground temperature. This sinking air is sinking only because of what is happening in upper air and the wind movement. This sinking air has got nothing to do with what is the temperature at 25 degree or 30 degree. But as the air is sinking, will it not get heated up ever so slightly? It will, because of the adiabatic compression. It heats up ever so slightly, but nonetheless, it hits the ground. When it hits the ground, then what will happen? As it hits the ground, it will divert into two parts. It will divert into two portions. One portion moves towards the poles, another one moves towards the equator to fulfill the vacancy created in the region around equator due to rising air column. Isn't it? Now, meanwhile, the wind which has started or initiated a motion towards the poles, will it be able to reach the poles? It cannot because of Coriolis force. It will start getting deviated to the right significantly. But nonetheless, as it is moving, you have origin of wind from the high pressure region of the poles as well, which is happening. So this wind is on a collision path to the winds coming from the tropical region. These winds, they will collide. And when they will collide, what will be the consequence? What will be the result of it? Winds, when they collide, what will happen? Will they dig underneath the ground surface to accommodate themselves? No. Will they simply bypass each other and reach the destination nonetheless? No. They will have only one path, that is to rise up. So the winds here will rise up. Now, as they are rising up, here also they will hit the tropopause. When they hit the tropopause, the winds will diverge. One portion goes towards this area. Here it collides with the wind accumulated at 30 degree. And due to that collision, this wind will simply drop down. Whereas another portion diverges and moves towards the region of the poles. And that fulfills the requirement of the high pressure. So overall, there's a circulation which is induced, but there is not one circulation as Hadley had propounded. There are multiple such circulations. And that creates multiple different pressure regions as well. Let us understand the pressure regions here. For example, in this area, that is 25 to 35 degree north and south. In this area, the air is sinking, the air is falling on the ground. So will it create or impose a high pressure on the ground or a low pressure on the ground? It will impose. Very good. It will always impose a high pressure on the ground. Despite the fact that at 25 and 30 degrees, you have very high amount of heating, temperature is high, still you have high pressure. Why? Because the air is sinking, and that sinking is independent of the ground temperature. That is why you have a consistent sinking. On the other hand, at around 50 to 60 degree north, here there's a convergence of wind, and the wind in that case rises up. What will be the impact of pressure on the ground surface as is experienced? Beautiful. You will have low pressure. Right? All of them. Preetham, but sir, in northern hemisphere, wind turn in right side. Then why to turn you in left? I am not turning to the left, Preetham. And where is it that I have indicated a leftward bend? Anywhere. Show me where is it that you think that the wind is deviating to the left. I hope that this entire circulation, you don't confuse it with the leftward motion. Okay. I hope you don't confuse this entire as a leftward. This is simply representing the one hemisphere. So here you have the creation of high pressure, low pressure due to thermal impact as well as due to dynamic movement of the wind. So these two areas can we say these are dynamically induced? Dynamically induced pressure zones. Whereas, can we not say that these are thermally induced pressure zones? Induced pressure zones. The entire image is slanted because the height of tropopause and the height of troposphere we have seen, it is not fixed everywhere. It is highest at equator and tapers as we move towards the poles. That is why. Yes, Prashant, that is correct. So let me repeat the entire process again. Okay, understand this. So at the region around equator, you have a greater heating by the sun due to which the landmass gets heated up. Now, as the landmass gets heated up in that region, the air also gets heated up. Air will warm up and air will start rising. It rises up till where? Up till the level of tropopause. And after that, the air will diverge. Air will diverge. It will move towards both the poles. But that motion will not be without any deviation. If I were to look at upper air circulation, let's assume I pick up this air column as it is moving. So it will experience a rightward deviation. It will experience a rightward deviation, isn't it? Now, regardless of how much air is supplied, it will always deviate to the rightward. And here you will observe, it cannot move to the poles because there is so much deviation, it eventually cannot reach the poles even. So all that air will start getting accumulated in this region. This is around 25 to 35 degree north and south. Both of these places you will experience it. Air keeps on getting accumulated. And because we are at the top of troposphere, the temperature will also be low. So you have now accumulation of cold air and it further keeps on getting accumulated. So it will eventually sink. It sinks and hits the ground. At 30 degree, it hits the ground. When it hits the ground, on the ground, it will exert a high pressure. Now, from that high pressure, winds will diverge. One will go towards the region of equator where that vacancy has been created. Where that vacancy has been created, from both the hemispheres, winds will rush in to reach that region of low pressure, right? And one will go towards the region of the poles. But the one moving towards the poles will encounter the polar winds, which are generated from the poles due to very high, extreme high pressure created due to the thermal conditions, very cold temperature. So that is where the winds will collide. Again, a dynamic involvement of wind pattern. And as they collide, they will be forced to rise up. So on the ground surface, they will create a low pressure. The winds will rise up here, creating a low pressure. As they rise up from the region of tropopause, again they will diverge. One will go towards the region of the polar area, the other will come and will further collide with the extra wind which is getting accumulated here at around 30 degree. So that will also sink. So that creates a kind of a perpetual circulation. So here, these individual cells, they represent the circulation that is experienced across the planet. Okay, so this is what we have as the tricellular model of circulation. This is a representation of the tricellular model of circulation. Now in it, each of these cells of circulation, they are named differently. This is named as the Hadley cell. This is named as the Ferrel cell. This is named as the polar cell. Okay. Is it important for mains perspective? Yes. And more importantly, if you want to understand the concepts of El Nino, La Nina, jet streams, for all of them, this is important. Indian monsoon, for all of them. Shivam, at 25 to 30-degree north, we are seeing accumulation of air, so we should see strong winds. No. Why do we need to observe strong winds there, Shivam? Accumulation of air on top. So there is a vertical motion of the wind, right? But if you are standing here, will you experience the winds to be crossing you? No, the winds will originate from where you are standing. So you will get a feeling of absolute lack of wind movement in that region. We'll come to it. Okay. Moina, why the wind air coming from 90-degree towards 50-degree? It is the polar region. It is this region. So from here, first of all, this is a high pressure region. And from poles, where will the winds go? They will always come south. And in this case, they will always move north. Isn't it? That is why. Wind, why do they bend? Because of the Coriolis force. Why these winds can't going above 2 pole? Because no wind can move 12,000, 15,000 kilometers and still be able to maintain its momentum. It is simply not possible. Given the amount of deviation that they will have, given the amount of frictional force they will experience, you cannot have one wind from the region of the poles to the equator or vice versa. Yes, Rahul, that is correct. And why only 3 circulations and not n circulations? Karthik, good question. But because of the thermal impact which is created at 0 degree and at 90-degree, these are the thermal cells, so to say, created due to temperature. Now, both these thermal cells induce a wind movement in between them. That is the Ferrel cell. That is referred to as a dynamic cell. That is why 3. Benita, why does divergence and convergence occur at 25 to 30-degree? Because that is the distance that will be taken for the wind to accumulate. Because the wind will bend. Imagine, can the wind accumulate here? No, it cannot. So, where the winds will accumulate, there only will it sink. Okay? We'll study that later, Pratyaksh, don't worry. Are there any particular angles in the cell? No. So here, when we talk about these circulations, they induce, as you can see, pressure regions on the ground surface. And also, as you can see, they induce surface movement of wind pattern as well. These winds that you see, these cover the entirety of the planet. So these winds, they will always be in circulation. And here, let's suppose we talk about the seasonal variation. Will these pressure cells or will these circulation cells be influenced by the seasonal variation? Absolutely yes. For example, if we consider the sun, let's suppose sun is positioned at the region above equator. That is today, equinox, sun is placed at the region above equator, right? Now from today onwards, sun will start shining slowly and steadily at a greater rate over the northern hemisphere. Let's suppose that on 21st of June, when we say of summer solstice, sun is somewhere here. Now, when the sun is in this position B, will the heating be maximum still at 0 degree? No. The heating will be maximum wherever the direct rays of the sun come. So that heating might come out to be somewhere here, this place. So in that case, the rising air column might be observed from somewhere here itself. Isn't it? So if the air column is rising somewhere from here, so then the accumulation will happen somewhere further north. So the sinking will happen somewhere further north because the rising has shifted. So the sinking will also be shifted. So like that, between the seasons, because of the shift of the position of the sun, the pressure belts and the associated wind patterns, they also experience a shift. I will repeat. In various seasons, because of the shifting of the position of the sun, there is different amount of heating which is received, and that is what leads to an overall shift in these pressure systems as well. So here, if you take a look at it, each of these regions, they represent a pressure zone. At the region around equator, where you have a thermal low pressure, this is also what is referred to as equatorial low. Equatorial low. It is a low pressure region. So equatorial low. This is an area where you have winds coming from the tropical region, that is around 30 degrees from both sides. Winds are coming from tropical region in this area. They are converging, they are rising up. More winds are coming from the tropical area, converging and rising up. So that is why this zone is also what is referred to as the intertropical convergence zone. Intertropical convergence zone, or in short form ITCZ. Okay, then the high pressure which is induced here, this is referred to as the subtropical high pressure zone. So despite the high temperature here, still you have a higher pressure, because here the wind movement is independent of temperature and it is the dynamic pressure zone. So this is a dynamically induced. Here again, despite the very low temperature observed at around 60 degree, still you have the creation of a low pressure that is referred to as subpolar low pressure zone. Because again, it is a dynamic pressure which is independent of the temperature. So that induces surface movement of winds between 25-30 to around 0 degree, between 25-30 to around 60 degree, and from 90 degree to around 60 degree as well. That is what generates the surface movement of winds. So as you can see, this is a depiction of the southern hemisphere. Southern hemisphere is also a mirror image of what is happening in the northern hemisphere. You will observe that around the region of the ITCZ, around the region of ITCZ, the winds will rise up because of warming, that is the equatorial low. Then they will rise up, they will accumulate here, they will sink, just like a convection current, that is the Hadley cell. So at around 30 degree, they will create a high pressure. You will have a low pressure at 60 degree, and again, high pressure at the polar area. Why equatorial low is considered to be ITCZ? Because at this region of equatorial low, you will have winds coming from the tropical regions in both the hemispheres. What are tropical regions? Tropics is the area lying between Tropic of Cancer in the north and Tropic of Capricorn in the south. That is what is referred to as tropics. So winds from both the hemispheres, tropical winds from both the hemispheres, are converging at equatorial low. That is why intertropical convergence zone. That is why ITCZ. Now all these basic pressure zones which are there, pressure belts as they are referred to, all of them, other than the polar one, all of them will experience a kind of a shift. And why is that shift? Because of the shifting of the seasons in general. Okay? Now, then the pressure belts Obviously, as you can see that between the pressure belts, they will induce the surface movement of the winds, and that surface movement of the winds, that is again going to follow Coriolis force here. So let me try to simplify this for you. So let's consider different pressure areas. Let's consider first of all the equator. Let's consider 30 degrees. Let's consider 60 degrees. 30 degrees here. 30 degrees to the south. 60 degrees here. 60 degrees to the south. And then the poles. Yes, Abhinav, ITCZ also shifts, as we will see in the portion of Indian monsoon. ITCZ comes over India as well. During, as we are talking about, in a couple of months, you will find ITCZ lies over India. Depends upon where there is maximum heating, depending upon the position of the sun. Around the tropical area where there is maximum heating, there will be the thermal low pressure. Now let's consider this 0 degree, 30 degree north, 30 degree south, 60 degree south, 60 degree north. Let's analyze the wind pattern. So, the surface winds. As we can see from the image, there is a surface wind moving from around 30 degree to 0 degree, and also from 30 degree to 60 degree. So from 30 degree, because there you have sinking air, wind moves towards 0 degree as well and 60 degree as well. So here, wind will try to move towards 60 degree as well, towards 0 degree as well. But they will experience deviation, isn't it? Deviation due to Coriolis force. So here, these winds, they will deviate due to Coriolis force. They will bend to the right. Here also, they will be bending to the right. Simultaneously, we have seen that there is a wind moving from polar area. So same thing will happen in the southern hemisphere as well. Wind moving from 30 degree to equator will deviate to the left hand side. And again, here again, excuse me, here again, you will see that it will deviate to the left hand side. Isn't it? Now, then after that, from the region of the poles to the region of 60 degrees, we have seen the wind is moving, which is converging with the tropical air, and it is rising up. So there is a wind movement like this as well. Right? Here also. Now, this is the kind of a wind movement that you experience. Now, these winds, as you can see, they are prevalent all across the planet, and they are present throughout the year. They might change in their intensity, in their velocity, in their position here and there, but they are persistent throughout the year. That is why these winds are referred to as planetary winds or permanent winds. Permanent winds. Okay? And these pressure zones, they are the ones which lead to this wind movement. Now, the 30-degree high pressure, this is also what is referred to as horse latitude. Around 30 degree, 31, 32, 28, 29, that is referred to as horse latitude. Why? Because if you imagine the ground surface in that region, let's suppose you have sinking air. Now, sinking air basically means lack of rainfall and everything. So, if you are an individual standing here, the air is sinking and is moving in both directions. So, for you as an individual, will you experience any wind movement if you are standing at 30 degree? What do you think? Absolutely no. You will never experience a wind movement. Your friend who is standing here will tell you that what are you speaking about? The wind is so strong. That friend might experience the wind movement, but for you, there won't be any wind movement. So that is why around 30 degrees, because there is a high pressure, there is a complete lack of wind movement. And that lack of wind movement historically and traditionally was suffered by many of the ancient sailors and mariners. So when the ships, the older ships, they did not have the diesel engines or the nuclear engines which could power them. The older ships would be powered by wind movement. Now, when there would be a lack of wind movement, the ships would be stalled in the same place for many days altogether in order to conserve food, resources, water. Water is the most scarce resource when you are moving on the oceans because you cannot drink the oceanic water, you will die immediately. So, to save all the resources, what the sailors used to do, what the mariners used to do is they would push off few of the horses that they would be carrying. They would push them overboard into the water for two reasons. One reason to conserve the resources, and second, when these large beasts and animals they will fall in water, they might create a splash in water which might initiate a movement of the ship. That is why these latitudes they are referred to as horse latitudes. Now, from the horse latitudes, you have the origin of wind, the movement of wind which reaches the region of 0 degree or equator. Now, these winds, they originate from northeast and southeast direction respectively in the northern and southern hemisphere. And they move significantly towards the southwestern direction in the northern hemisphere and northwestern in the southern hemisphere. This is the direction in general. These winds, they are also what are referred to as the trade winds or simply trades. Because historically, these winds have aided and facilitated the movement of ships and sailors from one portion to the other. So that is why they are referred to as trade winds. Trade winds converge where? At the ITCZ Intertropical Convergence Zone. Now, even there, where they converge in this region, this is referred to as the doldrums. Why the doldrums? Because here again, you will experience a lack of wind movement, a calm nature. You will receive rainfall, but there's a calmer, there is no great wind movement which is observed. Why? Because here again, understand this. Suppose this is the ground surface. Let's suppose the wind is moving at the region of ITCZ and it is rising up. Now, this zone, the entire area where the wind is rising up, do you think it will be a point where you can stand and you can see the wind coming here, you can see the wind coming here, talking to each other, discussing what we should do next in life, and then they start rising up? Do you think that is the case? Obviously not. We are talking about large columns of air movement which span all across the planet. So, this zone in itself will have a larger portion, a very large area spanning for many hundreds of kilometers. Now, in that region, the wind is rising. If you were an individual who were adventurous enough and you are standing here, the wind is moving, you will experience the wind. If you come here, you will experience the wind movement. But if you are an individual standing here, Will you experience any wind movement at all? Absolutely not. So that is why, because of calmer conditions, you will experience a lack of a significant wind movement. That is why it is referred to as the doldrums, right? But in doldrums, you might still receive rainfall because there is a rising air column. In the case of horse latitude, you don't receive rainfall at all because of sinking air. Now, from the horse latitudes or around 30 degree, you have winds going to 60 degrees. Now, what are these winds referred to? Winds, whenever they are named, they are generally named based upon the direction from which they originate. So here, if you look at the winds, the general direction of the wind is what? It is west to east. West to east. It is west to east. So that is why the winds in these regions, they are also referred to as westerlies. And then further, as you move towards the region of the poles, the general direction of the wind you will observe is east to west. It is east to west. And that is why here you will find the presence of winds which are polar easterlies. Polar easterlies. These are your permanent wind systems and the pressure zones associated with them. But then, if you want to really tickle your mind, if you want to really understand what really happens, as many of you keep on asking, that is this the real story behind it or are you hiding something? So, if you want to understand it, first of all, understand that anything which can be represented in a kind of a diagram using a scale and a circle, obviously, our planet is too imperfect to observe that. So, in reality, rather than now, when I'm saying in reality, for general studies, candidates are not expected to know the reality. For general studies, if you have an idea about the pressure zones, about the westerlies, trade winds, etc., be happy, have a celebration because you have understood a major portion. For general studies, nobody is going to ask you what happens really. But being a student of geography, you need to understand, you need to know what is the real scenario. In real scenario, in real life, rather than having this belt like portion across the planet, you have high pressure and low pressure zones. And those become the driver and the attractor of winds across the entirety of the planet. In reality, you don't have these pressure zones extending like a uniform circle as if someone has drawn it with the help of a map. No. In reality, what do you see is something very, very unique. For example, in the month of January, observe, rather than having the entire ITCZ spread over, you'll find that rather than this ITCZ spreading entirely, you will observe low pressure centers at equator. And it is not always fixated at equator. Over the region of Australia, look how ITCZ has come above Australia in January. Why? Because at this point of time, it is summer in the southern hemisphere. In January, it is summer. So there would be heating of the Australian landmass. Now, the horse latitude. Ideally, you would expect the horse latitude to be a uniform belt, right? But what is the reality? Reality is different. You have few of the areas of high pressure. Areas of high pressure. So these high pressure, they will be the drivers of the trade winds. They will be the drivers of the westerlies as well. Then, similar in the southern hemisphere as well, South Pacific subtropical high. Then you have the South Atlantic subtropical high, South Indian Ocean subtropical high. All these are what? A part of the doldrums, a part of the subtropical high pressure. Here also, they are a part of the doldrums. Then subpolar low pressure, that should also be uniform. But no, it develops only in certain areas around the Aleutian Islands, near Alaska, around Iceland, right? So these are your dedicated low pressure areas. So winds will be moving there, low pressure areas, right? So rather than a pressure belt, in reality, what you have is a pressure zone. Observe, in the month of July, this is what happens. You will find that the low pressure from the region of equator, that is not uniform anymore. It travels over to Indian region as well. And here the low pressure is back in the Pacific. And there you have the Bermuda high, or the Azores high as it is referred to. This is the subtropical high pressure, right? Here also you have subtropical high pressure zones. So that is how, in reality, you have this high pressure and low pressure zones. This you don't need to learn. This is only for those who want to know that what happens in real life, only for those informational purposes. You will be asked a question, if at all, you will be asked a question regarding the basics of westerly movement, the basics of the pressure zones. You are not supposed to deal with this specialized map. The only reason I have indicated this specialized map, this is something that I have not even indicated in the tablet lecture or any other lecture. This is because I want you to open up your mind. I want you to open up your mind that there can be a new reality, or there can be a new practicality from something that we are reading in the books, how it implements in the real life. If you get a clue of that, then you will be able to associate the real life happenings around you at a much easier rate. That is the only purpose of indicating this map to you. No question will be asked from this map. That is a guarantee. But it will never hurt you if you know that what is Bermuda High or Azores High, what is Aleutian Low, what is Icelandic Low. All that you will get from the map itself. Okay? Now, then we come to the portion of local winds. Till now, we have seen permanent winds or planetary winds. Why did we call them planetary winds or permanent winds? Because they were in motion continuously, permanently throughout the planet. Local winds, these, by the way, before this, when we talk about any new topic, the most important question in your mind is relevance for examination. So this is relevant for your prelims. Once UPSC has asked a question in mains from this, but it has been a long time since that point. In prelims, types of local wind, and at the end of the PPT, I will provide you, or I have included within the PPT itself, the entire list for all the local winds. So you should not face any issue. All the types of the local wind you will deal with there. And regions. Regions where experienced. These two portions, just you look at it for prelims perspective. This area, you don't find questions for GS portion at least to be asked in the mains examination. That will be more than sufficient. So prelims perspective, you need to know. Now, why are certain winds referred to as local winds? The reason is simple by the name itself. First of all, they are restricted to a smaller area. Restricted to a smaller area. And in existence only for some part of the year or some part of the day, right? Only in some part of the year or some part of the day you find that to be in existence, not across all the seasons. Now, these local winds can also be further subdivided into daily local winds and the seasonal local winds. So, when we say daily local winds, example, land and sea breeze, mountain and valley breeze, and valley breeze. And when we say seasonal, example, Lu, Chinook, Phone, Sirocco, Mistral, Harmattan, etc. So we will be talking about these daily local winds, what they are. We'll be talking about a few of the seasonal local winds so that you understand what do we mean by the seasonality. And then I will be having the entire list for you that you can go through for your revision purposes. Okay? Starting with the portion of land and sea breeze. Kivika, thermal and dynamic pressure still relevant in this map? Yes, Kivika. The Bermuda high that you see, or the Azores high, that is a dynamically induced high pressure. Similarly, the Aleutian low, the Icelandic low, they are dynamically created low pressure. Okay. Permanent winds direction, Pritam, haven't we seen that? Trade winds move from northeast to southwest, westerlies west to east, polar easterlies east to west. Okay. Now, then we come across land and sea breeze. Now, this existence of land and sea breeze is because of differential heating and cooling of land and water. Differential rate of heating and cooling of land and water. Now we have seen that during daytime, land gets hotter, water is cooler. During night time, land is colder, water is warmer. Now, this minute difference in temperature, that is enough to induce a kind of a difference in pressure as well. So, during daytime, what do you experience? Land is warmer. So, over the land area, because of higher temperature, you will have low pressure, and water is comparatively colder. So, here you will have the development of a comparative high pressure, isn't it? So here, movement of winds on the surface will always happen from high pressure to low pressure. Why? Winds always blow from a high to a low. So the winds will blow from a high in the sea to a low on the land. After reaching that low pressure, the air will be warmed up. And that air which has come all the way from the sea, that poor fellow, he did not know that he will also get warmed up. He warms up, and then where will that person go? Or where will that air go rather? Rise up. So it rises up and you have a convection cycle. So on the ground surface, let's say you are an individual chilling at the beach. You have reached the beach, that okay, I have attempted the prelims, let's enjoy at the beach. What do you experience during daytime? You will experience wind movement from sea to land. So here, wind from sea to land. And winds are named after the point or the direction of origin. So because this is originating over sea and moving to land, this is what is sea breeze. Conversely, during night time, land becomes colder. Now, as the land becomes colder, this develops a comparative high pressure. This continues to remain warmer. Sea takes a longer amount of time to lose heat, so it will still be comparatively warmer. As the sea is comparatively warmer, there you will have low pressure. Winds will blow from a high to a low. So winds are moving from land to the sea. So during night, you will experience land breeze. That is land to sea. By the way, please don't count this under offshore and onshore wind conditions, because here observe that the entire phenomena is only for 50 kilometers which is happening. 50 kilometers might be mighty in my life, it might be very huge in your life as well, but across the entirety of that planet, 50 kilometer is not even visible from the map. So that is how small this event is. So please don't count it as offshore and onshore wind movement. At night you have low pressure over water, because comparatively at night time water will be warmer, because water takes more time to lose heat. Yes, Preetham, that is correct. Kindly take a look at the annotations of the PPT of the previous module. We have written all of this. I personally have written it in the slide, so I remember it. Take a look at the annotation. We have written that why during daytime land has more temperature, why during summer season land will have more temperature, and so on. Then we come across mountain and valley breeze, again a daily occurrence. Now, why does this happen? During daytime, there is greater solar insolation which is received at the top of the mountain. Greater solar insolation. Now, by the way, in this, don't think about Mount Everest. Think about the normal hills and the small valleys that you have. Now, in this case, when there's greater insolation at the topmost portion, would you experience there development of a low pressure? Low pressure. Comparatively, during daytime, because the valley receives lesser insolation, so this will be comparatively cooler. So here, a comparative high pressure. Comparative high pressure. So automatically, there will be a wind movement, which is going to come to the low pressure from valley to the mountain. It is moving from valley to the mountain during daytime. Winds are named after the point of their origin. So if it is originating from the valley, what will we name them? Perfect, beautiful. So this will be what is valley breeze. This will be experienced only during daytime. And during night, there will be a loss of heat. Loss of heat. And we have seen in the case of valley inversion that top of the mountain loses heat at a much quicker pace because the air above it is very thin. So this becomes your centers of high pressure. Centers of high pressure. Now these centers of high pressure, comparatively warmer wind at the valley bottom, they will be driving winds to the valley bottom. Now, in this case, winds are originating from the mountain, moving into the valley, and hence they are referred to as mountain breeze. Good, Pranay. Now, see, there can be two approaches from your side. One approach can be that, okay, all this is there. I have understood it right now. One fine day when the stars are aligned, when the sun is shining, and when all my dates are aligned, that fine day I will choose and pick up this topic. I will learn it to such an extent that I will be able to vomit it as it is in the exam hall. The other approach can be don't learn anything out of it, but after the class, try to understand why that tricellular will be circulated, why that mountain or valley breeze will be generated. Regardless of the available annotations, regardless of the available videos that you have with you. If you really want to gain a mastery over it, I would suggest to you a very simple thing. After you have understood this, close it all up, pick a blank A4 sheet paper and start drawing the tricellular model on that blank A4 sheet paper. Try marking or labeling the permanent winds, the pressure zones. In the first attempt, you will falter somewhere or the other. Look at it again, where you have faltered. Understand why you have faltered. Draw it on your own again. Draw it on your own in the case of land breeze and sea breeze again. If you do it right now after the class, you will significantly be able to retain it. You will never need to learn it all. So many of the candidates I am seeing, you are following that approach. So that will be sustainable. And again, if you have the approach that, okay, I will do this, what you are saying, let that fine day come when the stars are aligned, when the sun is in position with the moon, and there is written on the sky, civil services aspirant, then I will pick it up. So that day never comes in the life of a civil services aspirant. Procrastination is the virtue that you guys will worship in that case. So try to pick it up as soon as possible. Revision will be easier. Okay. Now, few of the seasonal winds, seasonal local winds, if we can. When we say the seasonal winds, that is because they are in existence only during certain seasons. For example, here we take the case of Lu. Lu is the direct example of what we refer to as a warm advection. It occurs mostly during the summer season or only during the summer season, and that too not across the entirety of the country, but only to the northern part of the country. That is the region to the north of Tropic of Cancer in the country. Only in those areas you will experience the existence of Lu. Now, what is this? This is a dry wind, dry and warm. And where is it originating from? It is originating from the region of Sindh, Balochistan, and Punjab province of Pakistan. Now, from there, it moves over the Thar desert of Rajasthan. When it moves over the Thar desert of Rajasthan, it becomes more dry because it is moving over a desert area. It becomes more dry, it becomes more warm as well. Now, as a result of that, you will find that in the entire northern belt around Rajasthan, Madhya Pradesh, Uttar Pradesh, Chhattisgarh, Bihar, Jharkhand, West Bengal, in all those areas, you have a hot and dry wind which blows strongly during the month of May and June. Direction of movement is from west to east, and they are usually experienced in afternoons. They can raise the temperature around 45 to 50 degrees Celsius in any particular area. Okay, so that is what is referred to as Lu. That is where we'll restrict the class for today. Tomorrow we will initiate from Chinook, humidity, precipitation, and possibly we'll try to get into the portion of cyclones as well. Okay, Risha, see, Risha, basically, when you talk about the existence of a Lu, so here, let's say you have the Indian subcontinent. So it is from Pakistan that this wind originates around Balochistan and Sindh. This wind crosses the region of the Thar Desert. As it crosses the region of the Thar Desert, then it becomes drier and warmer. Drier and warmer. And it raises the temperature, and that is why it is suggested never to venture out in the afternoons. You will find that the elders in your family, they would always have suggested you, especially if you are living in these portions of the country, that never to venture out during summer afternoons at especially around 4 p.m., 5 p.m., because once you get exposed to this very hot wind, suddenly your body temperature starts behaving abnormally, and suddenly you fall sick, you can catch a fever as well. Okay. Yes, Dinesh, you can. Is Lu a local wind, Suparno? Yes, it is a local wind in the sense that it is a seasonal local wind. All those who have to attend the webinar, you can kindly leave. Okay. Um Ankita, friction force is the force of resistance which is offered. Friction force, the force of resistance. For example, even when the tire moves on the road, it gets a force of resistance. That is the friction force. Harsh, why there is high pressure on mountains in night? That is because, Harsh, mountain tops, they will lose heat during night. They will lose heat at a much quicker pace. Isn't it? Why? Because the air above them is much thinner as compared to the valley bottom. So that is why they will be able to lose heat at a quicker pace, become very cold, and hence high pressure. Siva, you have a basic question for how to approach editorials. See, if you want to make editorial reading easy for you, Siva, I would suggest, first of all, be daily or regular on a daily basis so that you get into the frame of mind of reading such long texts. Secondly, never read or never get carried away by the political editorials written by maybe chief of BJP, chief of Congress, chief of Trinamool, any political party. Don't look into that significant detail. Thirdly, editorials you will find are subdivided into certain paragraphs. Each of them tell you a different messaging. So your uh, effort should be to read individually and understand the larger picture painted by each paragraph. That will help you look at the entire editorial. Loo and heat wave both are same or not? Absolutely not. Absolutely different. Why Loo not going towards Iran, Rahul? Part of it is Coriolis force, but mostly because of extreme low pressure conditions created over northern India. During the time of May and June, these areas receive very high amount of heat. It is the precursor to the monsoon season. That is why. Abhinav, because ITC shifts in India during monsoon, there is more trade in ancient time. Yes. When we talk about Indian monsoon, we'll talk about it. Uh, what are some advanced magazines for geography? So you don't see, Chinmay, if you are asking this question, probably you are interested in the subject for an optional purpose. In that case, I would always say that for geography, if you want to increase your understanding, its relation with the day-to-day life, Geography and You is a good magazine. I recommend it for all those who are preparing for geography as an optional. But otherwise, if you want to look at any other magazine for general studies purposes, Down to Earth fits the bill. It talks about multiple geographical issues, agricultural issues, current affairs, dealing current affairs with the static. Down to Earth is a good magazine for that. I'm doing taking one topic, write it on my own. Pranay, that is absolutely beautiful. If you are able to do that, there is nothing that beats that. Is Loo observed in Maharashtra, Mera, during afternoon? We are also, yes, sometimes. And that too in the Vidarbha region of Maharashtra, not the Konkan Maharashtra. In the Vidarbha region of Maharashtra, in the area around Satara onwards, all the way till Nagpur, and in that entire area, you do experience it sometimes. Then, Dinesh, yes, more. See, for the preparation, whatever is doable, do that as far as basics are concerned, right? Do the bare minimum which you can do it easily. Bare minimum does not mean that, okay, newspaper is also not possible, reading is also not possible, attending the class and then going back is possible. No, you need to do something extra. Okay? Don't worry, Preetham. Analyze the questions where you have gotten it incorrect. You will slowly and steadily improve on that by studying it more frequently. See, the purpose of the test is to understand where you are lacking. Purpose of taking any of the test is never to see how much you have scored. It is always to see where you are lacking. All these are your practice matches. Eventually, when you appear for your prelims or you succeed in your prelims, or even if you fail in your prelims, nobody is going to even ask you what is it that you scored in the test series first weekend BHLP test. Nobody is going to ask you. It is upon how you take this for your improvement. Always keep that in mind. The final battle is between UPSC and you, and the battle hall or the battlefield is the exam hall. All this that you are doing is to prepare yourself best for that battle. Wind flow from equator to 25 degrees. So why it is accumulating there and not moving forward? Gagan, that is because the winds are deviating also, my dear friend. If the earth would not have been rotating, the winds would have moved forward straight to the region of the poles. But because the winds are deviating due to Coriolis force, that is why overall around 30 degree you will find a greater accumulation. Okay. Suraj, where Lu originates and why? So Lu originates during the months somewhere here. It is in this region. It is in this region that you will observe the origin of the Lu. Because of the entire area experiencing low pressure, this region will attract winds from Arabian Sea. When the winds come here, they find out that, okay, we have created a surplus here, but there's a deficiency in rest of the region. And that is when the winds, they start moving towards the other area. And that is where they will cross the Thar Desert. They will create a dry condition. Sometimes it is possible. Yes, Gagan, it is absolutely possible. Ayushman, ideally, I would say 1.5 hours to 1 hour 45 minutes, more than sufficient. Okay. So that is where I'll end the session here today, guys. We meet again tomorrow. Take care of yourself. Goodbye and have a good night. Thank you. Any questions remained unanswered? Don't worry. Our SMEs are here. Still, if it is unanswered, feel free to write to me or write us to IES Live. Raktim, if you're still there, send over that reminder, my dear friend. So we meet again tomorrow. Take care of yourself. Good night and goodbye. Thank you.